So we did talk and went through a couple of very simple static analysis exercises earlier on. So what I'm going to do is I'm actually going to jump down into, we won't touch assembly language yet, but we'll jump down into using the Yara signature language, and we'll also talk through, I guess, incorporate some of the metadata components that we learned from the previous discussions. And I did carry forward a handful of the, what's this thing? I'm jumping there. I did carry forward a handful of the topics from the last classes as well. So generally speaking, I kind of look at static analysis as a feature extraction problem. So the idea is that you have these files, you have these artifacts, they all have different kind of features in them that you're trying to pull out. In some cases, you don't actually know what's useful ahead of time. The goal is to come up with a system to be able to extract information from here. And so we played around with the strings tool and with the OBJDump tool in the earlier lectures. Those are two systems that have a repeatable method for extracting certain types of data from binaries. So you might extract like meaningful attributes, metadata, and so OBJDump did that. About the program structured data, we were able to pull out header information that included when the compile time was and what the compiler version was that linked the executable together. We were able to identify what in the metadata, what libraries it used and stuff like that. We also analyzed some of the portable executable file structure in that earlier class. So I kind of gave a few summaries here that'll come, or I should say a few bullet points here that were good examples of information we were able to pull out. One that I do have up here as well that I don't really think I touched on, but later on when we jump into like document analysis and things like that, it's the kind of author. So that type of information is present usually in the metadata of a lot of different document formats. So the other piece that we also extract is kind of unstructured metadata or just unstructured data. I don't know why I use the term metadata up there, but that's kind of like the strings data that we pulled out before. One of the big ways that I use to distinguish between these two is that I understand the meaning of the structured data. Like when I was running the OBJDump tool, we'll actually just kind of go back to here, right? So when I was, actually I don't even know if there's an exe on here, right? But yeah, I do have something here, right? So if I was to do the OBJDump tool like this, I know, say, what, I'll say, go to this one, right? I know the meaning of having this text in the file at this location. So I know what that means. I know what the effect of that is. That has like meaning to me. However, when I run strings and I'm going through something like this, right? I'll go back here to something like, you know, this one. I don't entirely know why this is here or what it's doing. I can guess because I know I can read the English language, but it's other than it being a message that has those English words, I wouldn't really be able to understand what the situation is that causes the program to generate this message, right? That would require further analysis of the program to actually try and apply meaning or basically tag or label each of these strings with their purpose. And we actually did a short exercise of that. I believe that was in the previous class with IDA Pro, or not IDA Pro, but IDA Free, where we were navigating the program graph, and we used the string section to find out where a string was referenced in the assembly code. So when we were able to do that, we were able to identify what function call it is that causes the string to appear. Or more importantly, we were able to assign purpose to the string. We're able to find some functional reason for it to exist. But typically, when I dump data like this, I don't have that information, and that's the big distinction between this view and we'll go back to the OBJ dump tool. That's the big distinction between that strings view and this one, where this thing is not only telling me what the content is and what the values are, it's actually telling me why they're there as well. So this format message A exists here because this is a function call from this library up here that this program uses for some reason. I apologize. I will say that the volume thing caused static last class, even though it wasn't being used for some reason. I have no idea what's wrong with the speakers in this room. So they did attempt to come to fix the projector, and they only fixed it halfway. So anyway, getting back to it, that's the big distinction I'm trying to illustrate with, say, the structured data and unstructured data. And so unstructured data I kind of look at is really at the core of like what something, really just kind of observing from, externally observing what a artifact looks like. So I gave some unstructured data examples we discussed in class. One of the ones is bytecode sequences or machine code, something like bytecode is kind of a generic term, so like machine code, your assembly language that's compiled, but also the Java bytecode, things like that. Any idea why I would classify this one? Say if you're trying to do a side-by-side comparison of two programs, why I would have that one be in kind of the unstructured data section based upon. So the reason I end up having this one in the bytecode sequences or machine code, that type of stuff in the unstructured section is that a lot of times making meaning for it, the reason why you have these 5 instructions in a row, or a lot of times the reason you need to do that requires some contextual analysis of the program to extract that information. So when you're looking for these things in different, when you're looking for the same, say, sequence of instructions in 2 different programs, it's very often not the same reason why they are both there. So usually you're trying to use that as a almost pattern match hook between the two, and then you'll end up analyzing when you get a hit why you're getting a hit in this new file. So that's kind of why I put it in there. I also added in here because these methods, or I should say these data types, as we get into the Yara pattern matcher later, end up basically being employed in the same or similar manner. So, so now we'll jump into the unstructured data extraction, which I did demonstrate earlier. I gave the strings tool, which is in Linux, as an example. What I'm going to do here is I'm actually going to give kind of 2 really easy recipes that'll be useful later on when you're trying to use this to do static analysis, to do feature or string extraction. So one of the key things here, and this isn't necessarily that intuitive, it's actually based upon a very kind of legacy implementation that's in the Windows operating system, but it's worth noting is that in Windows and in some other systems as well, they actually use both of these data encodings to encode what would be human readable strings. So if I was to go back to this ffdeck.exe, what ends up happening is it extracts these strings using the UTF-16 string format. So let me see if I can, there's a positional one here as well, I think, that I can pull out, or maybe not. Yeah, here we go. Dash T. Oh. Did I do that wrong? Dash T. D. There we go. Or dash T, say X. Yeah, so this tells me on the left-hand column where the position of that data is. So the reason I'm doing this is because what I'm going to do next is I'm going to show the raw dump of the content of the file, and I just wanted to figure out where one of these was located so I can show you how it literally shows up in the raw data. Because these strings themselves actually have a different kind of format. And then I'll just use. So, and then I'll go up from here because they're at the end of the file. So what we will do is we will grab something like this one. So these bytes, let me do this for you. Those bytes right there actually represent the word inter, that's basically the substring for internal name. What you'll notice is that the way this is encoded is that every other byte is a letter, is a ASCII letter, and then every byte following it is zeros, or the null byte. And so that's a representation that Microsoft has been using in a lot of their operating systems that kind of deviates from what's commonplace elsewhere on the web. And so that's the UTF-16. What it really means is that this value right here is one character. So the idea is that every character really takes up 2 bytes. That way, you can have, instead of only having 256 letters, you can have, however many letters that's going to be, 256 times 256. So that was a way of doing, of encoding Unicode until they ran out of characters, and then they decided to actually use other approaches instead. The reason I bring it up is, as you can see, this is just some generic program that was compiled for Windows, and it happens to use this encoding. So that's the reason why I give you 2 possible choices for doing your string extraction, is that you really have, when you're just looking at the strings, you really have 2 kind of data sets that you can pull from to get information out of the program, and both of them have valuable information in them. So now we'll jump into the Yara project. So it's a relatively new system compared to some of the other malware scanners. It's actually been adopted by VirusTotal more recently, so in the past 4 years or something. VirusTotal, which I'll be totally honest is, I believe, now a Google project. So technically it's some way owned by Google or adopted by Google. But they have a community of contributors and community of support as well built up around it. So I will say that compared to some of the other tools that you can find out there like vScan and ClamAV, which I have slides on in the lecture from the previous year, but I'm not going to jump into those this time. This one has a lot more adoption these days. So I will say that it also has a lot more overhead to it as well, because it has a lot more features. And a lot of people in the analysis community end up using it for doing malware analysis and also classification, which would be, those will be probably the big uses in this class for it. So rather than trying to use it to make like network sensors or something like that, we're going to be mostly focused on using it for categorizing and classifying malware. So here's an example of a YAR rule. I actually have a link to documentation here as well, yep, there we go, which I'll actually bring up for you all. Oops. So it's centered around a custom signature building language. So this, one of the neat things about it is that the author of Yara wrote this pattern matching language that has a couple of basically atomic, or a couple of data atoms. One of which is raw strings, which you'll see all the PT labels here are referring to raw strings. And then this A label that's up at the top right here, that one's also referring to a a raw string or bare string or whatever you want to call it. It has support for what's called regular expressions, which the language uses a variant of the Perl compatible regular expressions, if you're familiar with those. So if you've taken automata or something like that, you probably dealt with a very basic concept of regular expressions in that class. This language is built on top of that with some extra expressions that allow you to do very complex patterns. So we can go through this one. This is basically trying to match the word, or I should say the string if space exists, and then dot star means 0 or more characters following it, and then finally there has to be template period PDF somewhere after. So literally what this is matching is it's matching this string up to the, basically this string from the I to the T. And then followed by anything. And then, yeah, and then the word template period PDF has to occur somewhere after the word or the term if space exists. So it gives you the ability to have like really complicated expressions like that. So it has a lot of other, and we'll probably end up playing around with some of the other expressions that it supports as well. The next language term or add-on that it has is this one, which this one's actually kind of or I should say crunched together. But this literally allows you to look for binary data. So these are the hexadecimal, each pair of letter, or each pair of alphanumerics is a hexadecimal value for a byte. So the values 00 through FF are the acceptable values in there. So those that ends up allowing you to create strings, for lack of a better term, that can express byte values that don't occur on your keyboard. So I can match instructions with this. In addition to being able to literally label out very specific byte values like this, so this is a really long one, you can also use the pattern language to provide mechanisms for like for wildcards and stuff like that. So and then finally, after you've defined what each one of these basically atom types are, or atom tokens are, might be a good way to put it. Then you actually decide how you're going to match anything that contains those with a condition. So in this case, the condition says that I would like to match any file that either contains A, so either contains this string, or B, this binary string, so this byte sequence, or R, which is this pattern. So anything that contains one of those, or anything that contains two from this set. So either start in CD, or start in exist, or start in command.exe, you know, or CD in exist, or exist in command.exe, or CD in command.exe. So any of those permutations where you get two from this bottom set here is what this part of the term right here is expressing. So you can do real complex combinatorials there. We'll do this. So there we go. Come on. Scroller's not working. I was actually going to go to the conditions. So I'm going to zoom in. There we go. So that it's something that you can see. And I don't need the menu visible, but so right here it shows you that you can also have an expression for occurrence, or recurrence I should say. So in this case the example is the recurrence of B is greater than 10, which means 11 or more occurrences of the string B. The number of occurrences of A is exactly 6, so not 5, and not 7. Let's see, that's showing right here. You can also tell it to look for the string at a certain offset within the file. So if you're scanning files or whatever, you can say that the string A, labeled with A, has to be at position 100 and B has to be at position 200. So you start to build a language that if you already have some idea of the structure of binary data, you can start to express some criteria that require certain values being at certain positions in the file and stuff like that. Or basically a data structure being set up a certain way. You can also give ranges, right? So that's the other nice thing, is that you can give kind of ranges. So it gives you the ability to use, it's got some basically predefined functionality to be able to define like the entry point. So this is an example of something that is actually a feature that only exists for this, for these file formats. I will say that this type of capabilities is where you start to get into the structured metadata, right? Where you start to get into that this value needs to be plugged into the following slot in the program header. So that same kind of concept I was explaining at the beginning of the lecture, where you end up working with structured metadata and then also unstructured data, is also one that the author of this program started to run into gradually, and decided to come up with a better solution for. So this warning box that's up here is actually explaining that they took this functionality that was hard-coded into the unstructured data engine, they actually pulled out and they put into a completely separate framework that they'll be using in the future versions of it. I actually talk about that later on. That has a separate set of feature extractors for the structured metadata. So you still end up using, you know, using these things for a lot of the unstructured data and everything like that. And then you have a better, you'll have a more generic, more generalized method for expressing structured data comparisons or structured metadata comparisons. So they start to get into also the features that are very specific to exe files and things like that. Here's the sets of strings. So for instance, I can build lists like this. It basically says like, here's a list of like 3 different strings, but any 2 of them, those types of things. So it's got multiple different ways. So you'll see these 2 that you see right here, the half of one at the bottom and then the one up at the top, are roughly the same kind of thing. They just, by choosing different names, they have a different way of expressing the same concept. So as you can see, kind of what I'm illustrating here is there's a language that was built to be more than just kind of like a pattern matching language, but it's actually a kind of conditional classification language. So also they have, let's see if they have the keywords list here. They might not actually have it. Yeah, they might not actually have it listed entirely, but what you can end up doing is eventually, or you can look in the system and they have like a keyword list there that you can basically use to try and figure out what are all the possible combinations that I can do. So, but basically it has a lot of the logical things too, so it has the and, or, and not, and all those things as well. So you can use like a negation operator to eliminate certain conditions and things like that, or to come up with certain conditions that would be exclusionary in nature. So I'll say, because, and I stated this earlier, but because of this kind of the power of this expressiveness, the side effect of it is that it can get quite expensive sometimes, especially if you start building on a lot of kind of pattern matching approaches. So one of the other things it adds, this is a relatively new introduction, so I didn't go over it last year when we were using an older version of the software, but I will bring it in now. This is how you get access to a lot of the structured metadata, so that the PE module in here or the ELF module in here, both of those will handle extracting certain values from the headers of the exe files or the executable files. It has a module that if I was to take my malware sample and run it through a dynamic execution sandbox, there's a popular one out there called Cuckoo that generates a very specific report format. I can actually give that report to Yara in addition to my malware artifact, and then it will make matching decisions based both upon the content of the file and also certain structured content within that analysis report. There's also a number of other capabilities in there as well. The math one is very interesting because it actually provides the ability for you to implement a number of, I'll just jump into it, but implement a number of kind of complicated, complex mathematical analysis across parts or whole files and stuff like that, to then try and give you, maybe a heuristic or something like that. So you can feel free to go into each of these. I believe a lot of them, they have some backing, or they have some background in someone's maybe research project or someone's analysis that found that maybe this computation was a good classifier or something like that. So, or in some cases, like this one, the mean might be good for computing some sort of kind of baseline or distribution measurement. So, also gives like the range allows you to say, look for, this example here that it's giving is look for a file size that's within a certain range, or look for look for the file size I don't entirely know what all's going on there. But, oh yeah, turn the deviation from the mean between these two. So basically they built on a lot of different modules. It's actually got a language that allows you to implement these things. They're not a language. It's got a lot of shorthand that allows you to implement modules like this that can kind of extend the functionality to maybe do additional analysis using the pattern matching language with the unstructured data or the structured data, as well as allowing you to tokenize certain structured data that you previously may have had to write like a specific positional extraction rule for. So it's very extensible in that regard. The other nice thing too, so here's an example of me just, you can see this runs off the screen over here. I think I can, runs off the screen, but just pretend there's a parentheses over there. And so this is kind of a really short example where I sort of derived it from the previous rule I wrote earlier, but basically it's looking for these two strings, and then it's also looking for the import table. So if you remember, there's that import table that I was just showing you from the OBJ dump. It tells you that this program uses this DLL, and then it specifically uses this function from that DLL. So the DLL has a whole bunch of functions. Not all software that imports this DLL or uses this DLL uses this function, and only the programs that were linked and had code calling this function will have this line in there. So basically, this says match. Logically, when I would have done the analytical work, I would have come across the case where these two strings, so this weird connecting to %d, and then it looks like they put in 2 dots and they meant to do 3, but they accidentally inserted a space here. So that string is present in the file. I have a modifier here that allows me to tell Yara to do a case insensitive search. So that's what the no case is, which you may have seen on some of the other rules is, do I want to literally look for that string, or do I want to fuzz it a little bit and allow for the uppercase and lowercase variants of some of the alphabets? Likewise, for this one, it also has to have that sequence of binary bytes, or sequence of bytes, and then also has to import this DLL, and also has to have this function from that DLL, and you can chain them just using your and or joiners. So to basically build really complex logical rules. So I don't know what the kind of finite size is on the logic chain that you can build, but it's pretty large, and you can even use like parentheticals and stuff like that to kind of group, say, sets of combinations together, so you can get the, like logical injunction, logical conjunction, or disjunction and conjunction. So the other thing that's neat, and this is actually distinct from, so you saw the C API that I showed you for the modules that was over here. So this was specifically if I wanted to write a module to extend the language, then this API allows me to take the whole language and then integrate it into my larger application or larger program. So I could write a program that does a whole bunch of things, but then also I would like part of it to use Yara for, say, satisfying a certain feature set or something like that. So great example. I think I put up here like vscan, clam scan, or clam AV. One of the nice things that the author of Yara did is that at its core, really, it's a library. So the author really wrote the library as a standalone thing, and then the tool that you will run on the command line. So when I go over here to back here and try and log in, I'll just run it from the command line really quickly so you can see. So this tool itself is actually a kind of front-end wrapper that he wrote that actually imports the library. That structure is also very nice because it enables it to be very like to be something that you can integrate with anything else. So the API is relatively straightforward, and I decided to give like a really quick 4-step recipe that I've used to be able to get from I just imported I just included the header, which is up here at the top, the 4 steps that I basically need to do to get to a point where I can have a set of have a compiled signature set that then I'm using to go and match data in memory or in a file or something like that. So with this shorthand on the slide, that'll be kind of useful when we do start working with this pattern matching engine. So above any of the others, we'll actually be applying this particular one in addition to some of the other tool, some of the other analysis tools like OBJDump, strings, EXIF tool. We'll be using this one a lot to be able to accomplish some of the more complex matching later on in the class. So this is kind of continuation from the previous one. So after you've loaded all the roles, which are literally just a bunch of files that contain those programs, the pattern matching programs I was showing you, then scanning really involves creating a callback function, and then you give your callback function to the to execution of the scan functions, and you may have to call it in order to say iterate across multiple files or multiple data arrays or something like that, and it'll basically run, and every time that it makes a match, it'll call your callback function. So how many, I guess a good question is, how many people in here have experience writing in C or C++? Okay, yeah. And how many of you have had to implement basically a callback API approach? Okay. Yeah. Okay. Yeah. So literally, what you end up doing is you pass a function, you pass the address of a function, and that function has to adhere to a certain API. So it has to accept a specific set of arguments that are given by, say, in this case, Yara. And then what will happen is you'll call this Yara function that you gave your callback to, and then Yara is going to go and call your function for you every time it has data ready. So that's a very common, I believe the Windows API is most notorious for using it extensively for a lot of the code. Yes?
Will Yara call my function whether a match has been found or not? Or
so the question is, will it call the function whether a match has been found or not? I'll jump, since I will have some time, I will jump in there to the most recent documentation to try and determine if there is actually a a callback function implemented for the non-matching case, because I can't remember if they actually implement that or not. I know some do, where they basically implement a I didn't match anything callback, right? So, but basically it'll keep running. So it'll be stepping. Say you have like a terabyte file or something like that that you want Yara to scan. It'll walk through that file trying to see if anything matches. And as it's scanning down, it calls your callback function. And then your callback function basically does whatever you need it to do to report and record where those matches are, and then after that finishes, then it steps on to the next bytes. So here's this is again what happens in the hit case. So inside of that callback function, you would want to implement something to handle this data whenever you have a match event occur. So the other thing that's nice, because it's a C library, is that they also wrote a Python wrapper around it. They also wrote a Go wrapper around it, and I don't have that up here because I don't know Go very well. But they have a Python wrapper around it. So you feel free to use either of these to your leisure. I will say that this is the most featureful, and you get the highest level of control to like Yara's internals with this. The Python API actually provides you with a very sanitized, a very contained version of the, or I should say, a very sanitized subset of the functionality that's available in the full C library. So they only really implemented the handful of functions that can get you very quickly from I have a bunch of files to I want to match something on them, but they did not implement all the possible features that are available in the C API. So the other thing that's different about the Python approach is that if any of you have used the RE library from Python, how many of you have used that? Okay, so those of you who have used the RE library, the regular expression library, what it basically does is, this is a great kind of analog to it. So what I do is I give it the patterns. In this case, I'm giving it a YAR rule. So I give it that data, and then it compiles, and then over here it fills this rule structure out with basically a matcher. And then I take that matcher and I call its match function on the unknown data, the large terabyte file that I have. And then what it does is it fills this matches list. It's not really a list, it's actually an object that contains a list. But you'll interact with it as if it's a sequence type almost. It fills it with all of the locations within my 1 terabyte file, for instance, where the data matched, and it'll have a specific kind of match object in there. So I think one of the questions that came through was what tool do I use the most as a malware analyst? I'll say it varies really. This particular one, I end up using a large amount for doing the static analysis because I can build very targeted signature sets, very targeted pattern matching signatures for it. However, a lot of times we're collecting the dynamic execution. So a lot of times I don't necessarily just want to look at what malware appears to look like. I also want to see how it behaves. And that's actually going to be something we'll cover later on in the class, but just kind of give you an idea. This tool, if you want to jump ahead, actually has a pretty straightforward installation mechanism and everything, as long as you have a Windows image to give it, that can automate the process of starting up a VM, running malware inside of it, collecting all the behaviors that the malware did, or I should say just collecting all the behaviors the VM did, because it doesn't necessarily separate background activity from malware activity. Documenting those in a nice structured report, and then shutting down the VM and then reverting it back to the original state. So that sequence of steps, which will become a real common loop for you to do as an analyst, is built into this system. So if you're looking for how to jump ahead on the dynamic end, and what I would recommend as being kind of what's most commonly used out there, this tool for doing summary analysis is out there. And so the other question, thanks for sending the questions up there. That's super helpful. So I think the other question was asking about endpoint security and stuff like that. So a lot of the topics that I'm discussing right now will cover some of the endpoint security features. CrowdStrike Falcon Host is listed in there. There's also Endgame has an endpoint tool, and then Carbon Black has another one. I do not have samples of any of those things for use in this class. I also don't, I don't have a huge amount of experience in those because I don't typically work in that space. However, there probably are other folks, some of you who may have friends who've worked in co-op jobs at some of those places, or yourselves may have worked in that capacity, may have worked with those. I do believe a lot of them are compatible with like the Yara, or even have Yara built into them. So one thing I'm aware of is CrowdStrike's Falcon Host was mentioned here, so that's one I'll go with. They use one of the signature engines they use under the hood is Yara. So ostensibly, I don't know what customizations they've made, but ostensibly, any patterns that you write in here should be, somewhat translatable to something like Falcon Host if you were to want to use it. I can't tell you how much further work would have to go into converting it, but we will be using a lot of tools in this class that are very applicable to the kind of security analyst community in general. So hopefully that answers your question. I believe that the behaviors that something like Cuckoo will report are also something that are also something that you might be able to capture in other facets of those tools. So basically the behaviors, the execution level behavior, the sequence of events that occur on a VM because of malware. I do not know how to translate those in any specific tool. So we'll be talking about how to read the reports and how to read the activity, and even ways to build kind of a noise filter or background like baseline out of these tools, so that you can help yourself identify the parts of it that are related to the malware and distinguish from the parts of it that are related to Windows background noise. So, but yeah, and then that's the end of the slides for today. But I was going to go and just kind of, here we go. So I'm going to go and jump in here because I do have, I do have it already set up in here. So one thing that I might end up jumping into is just to, pull out the strings, so the wide strings that are in here. We'll just kind of attack these right now. And one thing I'll also show you is let me do this. So I actually have on my system, I installed the Wine tool so that I could run that older version of IDA free that was only Windows. So we'll actually go through that. And I'm kind of doing this from the command line really quickly, but so basically I'll try and get a list of all the EXEs and DLLs that are in there. Really I'm doing this just to kind of show you like how many of those files are in here. So there's like 14 you know, 1476 of these, right? So maybe I'll look at this guy. Right? And so maybe I can do like strings on this guy, and it's like it says wine placeholder DLL. So I don't entirely know what all's in this file, but I do know that there was a somewhat, yeah. So what I'll do, the other thing I can do with this tool is I can actually give it a longer number if I want. So I can say like 8. That tells me only show me stuff that's like 8 characters or more. So, you know, maybe what I could do is I could like grab like, you know, 2 features from this and start there. So remember I said that there was like 14,000 and some, or 1,400 and some. So maybe I can go and grab this. I'm not sure if this is going to help. So and then I'll just kind of give it a any of them. So the idea here is that any string that matches, so any file that contains that string in it is going to match, right? So I might do, so remember, I can always get the help if I need to, but the big one I'm going to try and do is I want to try and see, is there a way for me to go and get that file from my 1400 set? So there's this kind of recursive thing here, which I'll start with, and then also it allows me to either look in a file, a directory, or a PID. So one of the other nice features of Yara is that not only can I have it scan files on disk, I can also have it scan process memory, which is our real cool feature. So if I have a lot of processes running in memory, and as we know, programs can modify their memory at runtime without necessarily having to modify the file on disk, right? That gives you the ability to search on disk, but also search in memory if you have administrative level access to the machine. So I might try and do, you know, this. So right, it's going through, and now that's a lot less than, you know, that's a lot less than it. So what's happening here is it's telling me, I should probably jump into what this is saying. This is telling me the test rule, the one that I named test. I said rule test, squiggly bracket. That rule, because I can put multiple rules in a single file, matched all of these files, and that's far less than the 1400 that I showed you. That is actually, we'll just do this, 31 files. So I've narrowed my set just by looking at that one feature down to 31, one of which is this WinHelp 32 file. But I still want to go further, so maybe I'll try looking at this, right? So maybe I'll try this thing and see if this one also exists. So and then I'll say, well, I'll stick with any of them for now. So we'll actually see what happens if I just kind of add. So what I'm doing actually now, just for the heck of it to see what will happen, is I added another term that'll basically be an OR relationship, because we're going to see if any of them will match. I'm adding something that's actually going to expand my filter a little bit further. So we'll see if that actually changes anything. So, and it doesn't. It looks like that doesn't change the matching at all. Now let me see if I do all of them, right? Now there's 3 files that match instead of 31, so I've dropped it down, and really it's just these kind of 3 files. So what I've learned here is that that one file that I thought was suspicious, and we're just kind of using this as a stand-in for a suspicious file. I know that this is a totally benign file. But not only did I build a signature that can directly identify that file, that signature was able to also tell me that that file was installed in these other locations on my file system too. And so that type of operational cycle is a lot of times what you'll find yourself doing if you do happen to be in a kind of malware analysis incident response role, is that when someone suspects something is wrong on their computer and they suspect they've got an intrusion or compromise or something like that, they usually don't say, and here's all the data I have that is related to the compromise. They say that I found this one thing that shouldn't be there. And they give it to you, and you have to analyze it. And then after you analyze it, you then have to blast it out, and you have to go and find out if you can find that bad thing anywhere else. Because chances are, if it's in one place, it's in 5 places, or something like that. And that cycle is a lot of times what you're going to run into. So this, I felt, was kind of like a really good exercise to kind of introduce that. That's kind of the I would say the operational cycle that you'll end up using this tool in if you end up having to use it in the field. We'll also be using it for a lot of like classification, but those classification exercises are going to center around this. Center around, can you pinpoint the thing that we want to get out of it without including a whole bunch of extra stuff that we don't want, that shouldn't match or that isn't bad. Or a better example might be if I'll just go to I'll go to Firefox, and I'll just go online, GitHub, Zeus, right? Here we go. So again, they say Zeus Trojan horse. It's basically a backdoor. So this is actually a really old family of malware. I like this page, which is, I always remember. So as you can see, I use this one for a lot of examples. So, there's Zeus malware. Let me see if, here, this is a great example here. Let me see if I can control. There we go. Okay, that's not. You can't read it anyway so well. So basically, so this is actually just an upsampled image, so it looks terrible. But basically, what they're showing is that they have kind of they're explaining how the malware fits into this larger criminal enterprise to steal money from people's bank accounts and everything. So they basically give this nice kind of supply chain almost. And of course, they draw it over the world because the idea was it was a big global, I don't know if espionage ring is the best way to put it, but basically financial criminal ring. And this Zeus malware that I brought up is actually was very core to the whole operation. So at some point in 2010, this used to be sold on the internet. Some point in 2010 or 2011, I guess is it, because this is the original leak site. Someone leaked the source code for this on the internet. So since then, it's been modified heavily and incorporated, or parts of it have been incorporated in other tools. But bring it up here because it's a really good example. So you got the source code here, which means that you could hypothetically, so here's your SLN file, if you're familiar with Visual Studio. Hypothetically load this up in a Visual Studio and start compiling it, and then start turning on and off different options and everything like that, and basically generate a large number of reference samples, which then you can use to, and a lot of people actually do, this is how So this is probably one of the key reasons why this malware is no longer in popular use, is because it's so easy now for someone to do research and basically compile a bunch of different versions of it and then build a large, like, broad detection system around it. So there's a lot of other tools whose source code has not been leaked that people have moved to. But this one's a good exercise because you actually can see the different capability that goes in there. That's probably not a great place to look, but source is going to be where, so you can see common, and so they have all of these. It's a C++ program, so and they have all these custom implementations of various different things. So they have like back connect bot, certificate store hook, so some sort of tie-in to your Windows certificate store. So they, I guess, have some mechanism for that's built into the tool for actually gaining access to that. VNC, well, you're probably familiar with, virtual network client or whatever, but basically remote desktop, right? So it has the ability to do like tunneled remote desktop. Trying to see HTTP grabber, so it has the ability to monitor your web requests and everything like that, and then grab things that are interesting. Screenshots, report, software grabber, so even grab like just what software tools are installed, that type of thing. So this one's really neat because there's all these routines that were written by someone and then refined over time. So these were written once a long time ago, probably in the early 2000s, to accomplish whatever the given task is. And then over time, they were refined and refined and refined and refined. And so now you see some of these are stripped out of the Zeus program and actually maybe ported and incorporated in other tools. So doing research on this one does help with trying to help identify derivative works. And so all of these functions that are in here now, I'm trying to see if I can find a good one that has like, yeah, so this one right here might not be a bad one. I forget what it does, the things over at the top. But the key thing here is that it's got a couple branch statements. It's got a while statement that's looking for a certain function call to return a certain value, and then it's got about it's got a really long sequence of invocations that happen after that. So from my perspective, I'm trying to analyze, say, logic or algorithms to figure out like which ones might be a good signature of copy pasting this code elsewhere. This might be a good one to start at, because also the other neat thing is that it has a list of these conditions that are based upon doing a comparison of very specific bit masks. So you could say look for the comparison or the combination of the comparison and the bit mask operation. So remember, for those of you who've taken assembly language, this will probably be intuitive, but to anyone else who hasn't taken assembly and hasn't done C, what ends up happening is you have one operation that ends up doing this bitwise and then another operation that ends up testing the result of this to figure out if it was 0 or not. And then a third operation that actually will branch the code depending upon what that test, whether it failed or succeeded, right? So for each one of these things, you end up having a very specific mask, test, jump operation, conditional jump. So you basically have 3 of those to test off of. And then on top of that, you have a handful of other things such as these here are going to be all constants that are being passed to these function calls. So these function calls have a very specific API, which is going to show up as data setup in the assembly code. So those are also other key unique properties to this, or potentially unique properties to this, that would make good avenues for, say, investigating how to write like a binary pattern one of those numeric binary patterns.